Okay, so we're at starting time. So what we're going to do together is this bottom one. So we'll walk through that with practice, just to give you an idea of what's going on with our nomenclature. Before we do that, what I want to draw, what I should have drawn your name or attention to was something else there. This is our primary side for nomenclature. Is now saying look at a structure and try and come up with the name. Okay? All of that breaks down to individual sections and pieces as you go through and process it. Your overall steps are in that blue box. Right? That's how you put it together, and then you try and kind of bounce around between those individual pieces. This next slide, I would argue, is probably equally important, and what it's looking at is now looking at the name and trying to go to the structure. So they're kind of inverses of each other. I will point out, particularly if you're looking at it in here, that the quote-unquote shape really only applies to one shape, and that's cyclo. So I don't know why I'd write cyclo again. That's looking at ring shapes. We'll talk about ring shapes a little bit later today. So if you're seeing a ring, you need to include that cyclo term into this. Okay? So what we're going to discover is some of kind of the troubles potentially with names is that you will find you can write a name wrong but still draw the structure. Right? And according to IUPAC, that means the name is wrong, period. It doesn't matter that you can draw the structure. You didn't use the proper rules, and therefore you are wrong. Right? And that is a very challenging thing to deal with nomenclature, but the theory behind it is sound. It's good. It's just almost impossible to actually implement. So IUPAC is the one that decides all the naming rules and all of those systems, and their intent is that for an individual structure, it has one name. It doesn't matter which orientation it is in space, it will always have one name. Okay? And if that were true, maybe I'd put a little bit more weight behind nomenclature. It's not. Nearly every compound has 2 or 3 different names. Okay? And that's mostly because you can't get people to agree, is really what it's boiling down to. And because we can't get people to agree, we end up having to deal with so many different names, and we have to just kind of accept that. Okay? Hell, my name, we can't even get people to agree on. Is it Mike or is it Michael? Is it Professor McFadden? Is it Doc? It's not Doctor, so you shouldn't be calling Dr. McFadden, but I get that one too. There's so many different variations on how someone would respond and how you could even talk about an individual and still have that information get passed along. Nomenclature is attempting to do that through one name to streamline that conversational piece. Okay, it's nearly impossible to go through and do. So if we're starting with now the name, we're going to look at the bottom one. Where should we start? Where would you start trying to process that name? You can mention colors, numbers, anything. Where do you think you would start? Okay, and this becomes one of the fun things. Okay, at the hex, you start in the middle of the name.
What's the main name?
Okay, and that comes, I think, from training and watching videos, is that's probably the easiest place to start. The main chain. We find the root structure. Once we have the root structure, we can then start adding things on top of it. Okay, that's a good first step because you aren't referencing the 3 or the stuff in front, even though that's the first thing we read. Which is good because most students start there. Don't start there. Main chain, so we're looking towards that end, we're looking at that hex. What does hex mean? 6 carbons, so we can now draw 6 carbons. 1, 2, 3, 4, 5, 6. You don't need to put the points on it, that's just something I'm adding to try and emphasize those points, and it helps me to count out the carbons as well. Okay, where should we move to now? I would argue no to the branch. What's the, well, she started to say define. Yeah. When I start at the hex, I'm starting there and I'm processing the whole rest of that name first. Okay? So if we looked at that as an order, this would be 1, 2, 3, 4, 5, like steps out. Once I've done that, then I'll look at the other part, and more than likely, I'm actually going to start in the middle there and jump, and then jump. So since it's the next step, I'd say A, B, C. Okay, so when we're processing this, we're jumping all over the place. There is no one right way to do it. It's as long as you get all the information, that's fine. That's just how I see it and how I process it. It allows me to move through it more efficiently. So hex, 6 carbons. The next thing in this is the ane, right? That's officially our hybridization. So the hybridization of our carbons should be sp3 through the backbone. Okay? There are sort of exceptions to that. Let's not stress about those right now. Okay, but that's the primary system. So ane hybridization, we're done. We're just saying there's no double or triple bonds in the backbone. The next thing I see is a 2. Okay, and even that I would probably skip. I'd probably go 1, 2, and then jump to the all, and then go back to the 2. Okay, because the 2 is really just a locator. Because I have nothing defining which way I'm numbering here, I can number it any way I want. So I could number it starting with the 1, doing it in blue, here, right? That's perfectly acceptable. That is no different than numbering it the other direction. Here's a bit of test-taking strategy, though. Right? If we're going to look at a test, the whole point of the test is, can you figure out the structure from the name, okay, or vice versa? How do you read? How do you read? Left to right. And if we put the answer choice in where it is numbered left to right, what could you accidentally do? Get the answer right. Okay, we want to minimize that as much as possible as test writers to make sure that you can't accidentally get the answer right. The whole point is to prove your knowledge. So almost universally, when you look at multiple choice, and it's not a guarantee, but almost, you're probably looking at 60% of the time, the numbering is going to go the opposite direction, right to left. Because that requires slightly more cognitive load in how you have to process this that isn't just natural reflex. Because when we're testing, we don't want to see natural reflex. We want to see what you learned about the content. So we want to avoid natural reflex systems. Does that make sense?
Does the way you read it though kind of change based off the substituents? Like where the closest one is, you start on that side?
True, but at this point, and so what you're talking about is going from structure to name.
Yeah.
Right? Here we're going name to structure though. So since we flipped it, your argument, which isn't an argument, an observation, isn't really valid anymore. Because what we're trying to do is say we've got the hex and now we want to hang things on it. We can hang things on it any direction we want, numbering right to left or left to right. Okay? We choose that kind of randomly or arbitrarily. Okay? A test isn't random or arbitrary. There's thought that theoretically goes in behind it, and if you know that thought, that can help guide how you should approach and set up your initial answer or your initial response. Kind of, sort of. Okay, so since I've now got my number identified, I need to reference my last piece, the all. What is the all a functional group for?
Alcohol.
An alcohol. And what is the alcohol? It's an OH. More precisely, it is a carbon bonded to an OH. I see your hand. And that carbon is sp3 hybridized. Yes?
So, for the test,
Yep.
because I've done all the play posits, I've read all the things,
Yep.
I've talked to you, I did not know that the OL was alcohol. So am
Okay.
I memorizing
I-
that whole sheet for the test?
So, and that's what I said in the last class. What I need to remember to do is to take that
Okay.
sheet,
Okay.
probably shrink it so that it doesn't take up a whole flipping page, and then put it at the bottom of the front page so that you don't have to worry about
And then
memorizing it.
how do we,
The next exam, and every future exam,
No.
Now you need to have it memorized, because we'll actually say, these are functional groups, this is why functional groups exist, this is why they're important, you need to know what they are. But for this first exam, I'm not expecting that, so I'll give you that slide. And we'll flip back to that slide, but I don't want to delete all my work.
Okay, can I ask one?
Yeah.
So, again, I've practiced this a bunch. I have not seen a question like this with the OL. Knowing that you go the full carbon group, and then I didn't even know that it could continue after the full long chain. I haven't seen a question like that on.
What do you mean? So I'll say right
And
away.
like a lot of the example problems.
This was in the play closet.
I know,
So.
and I did it, I took all the notes.
It's okay.
It just didn't come up in a lot of the practice questions, so I have never seen a practice question where we place the placement of the functional group also, so it seems foreign to me.
So
I'm
most of the
curious how
practice
this-
questions that you've come across are alkane based.
Yeah,
You're right. You did place the functional group. What was the functional group?
was the alkane.
The alkane. So you wrote A,
So
N,
you're
E.
putting, okay.
Okay. And we'll go back again to the summary slide that shows this, that is specifying that extra information on how we would change that. Again, I've got work here. I don't want to delete that work, but I will come back to that. Okay. So at position 2, what do we need? We need the OH.
Is that how you would write it on the test?
What do you mean?
With the O-H? Like, can it
Um,
be that?
As opposed to showing it
O-H,
OH?
yeah.
What's the difference?
Is one positive and one's negative? I don't remember.
It's a really simple thing. What's the difference between writing it OH? And
You're
OH.
just showing that bond?
There it is. That's all it is.
Okay.
You've decided that you want to be explicit in showing that bond. Do you have to show that bond? No. It's going to come down purely to choice.
Okay.
Okay. Later on, so like right now, it's actually interesting that I actually showed it. I'm going to bet that's a reflex from teaching OChem 2 yesterday. Okay. Writing it as OH here doesn't show us the bond. If we're going to talk about chemistry and where the electrons move, that's the most reactive bond. That bond is going to move around. And if I have it implied, can I show that bond move?
No.
No. So I will tend to reflex to showing the bond so I can do that chemistry.
Okay.
You'll notice I don't show the H's on anything, on the carbons. Why not?
Because that is just too messy, so you can imply.
So it can go to messiness. It's also, they're not reactive. Okay? Since they aren't reactive, I'm not going to bother to show that bond. Okay? And there are cases that will bite me. Like that's going to be a problem because sometimes they are reactive. And it depends on those very particular scenarios. And that's usually where I would encounter the scenario and then be, dang it, I got to show the hydrogens. And then I would backtrack. Okay? But the OH bond itself is one of the most reactive. When we talk about functional groups in the next unit, we'll start to understand why. Right now, how you decide to show it is entirely up to you. How it shows up on the exam, kind of random chance. Being explicit with the bond or not. Okay? Now that we've got our main name established, we can go through and deal with our substituents. Okay? I'm going to admit I'm probably choppy all over the place with dealing with those substituents. I might go with the locator instead of the core substituent name. It's just going to be kind of a whim. They're roughly equivalent. If we go with how I've labeled it, we're saying we're starting with the methyl, okay? And really, we don't care about the YL. What is the YL telling us? It's a substituent. Well, at this point, we already knew it was a substituent. We already identified the main chain. Okay, so what we care about is the meth. What does meth stand for?
1.
1 carbon. So I need a 1 carbon somewhere added into this drawing. I've already accounted for the main chain, so I can't say it's this 1 labeled as carbon 1 out here. I can't say it's the 6 labeled out there. Those are already identified within the hex. So it has to be somewhere else. Where else is it? That's why I have to jump to the locator. The locator says 3. So at position 3, I need to put in 1 carbon. Ta-da, there's my 1 carbon. Okay. Can I show it as a line? Yes. Can I show it as CH3? Yes. Would I ever show it as C with 3 bonds to all those H's? Probably not, because those bonds aren't particularly reactive. Why would I draw it as a CH3 as opposed to just a C? Or I would never draw it as just a C as opposed to just a point. I'm just trying to emphasize the fact that there's a carbon there. So it comes back to what I want in my drawing. Okay? Which is then going to go to you as the drawers. That's right, drawers. Artists, let's go with artists, that sounds better. Okay? Deciding whether you need that information or not. That's up to you. Okay? We might then also bounce back to this die chilling out in front. What does that die mean in front of the methyl?
2.
There's 2 methyls, okay, which means I need another methyl. Where's the other methyl go? And
Branches off of it?
this is an interesting question. I'm going to pick your statement. Branches off of it, like up here. Okay, if we put it there, what's the substituent now? That's the thing hanging on. How many carbons is that? That's 2. Is that methyl? No,
You just do a double.
that's ethyl.
side by side.
Okay, so then the other option, I'm going to have to erase all that, is that maybe it's supposed to go here. Okay, now we have a dimethyl. How did you know it belonged there? But what's the locator for? The locator is for every single substituent. You have 2 methyls, I only have 1 locator. That's a problem. Note, each of these names is wrong. Okay? So this name could be wrong in one of 2 ways. 1, we need another locator. Okay? Let's say that this is our correct drawing. We want this. What's the other locator?
3.
So I have to include another 3. Okay, and you might, well, isn't that redundant just saying 3, 3? But you're referencing every single methyl, every single substituent. Even if it shows up at the exact same locator, you have to specify that locator to remove all ambiguity. Because the other interpretation of this as our error is the die, and it shouldn't have been dimethyl, it should have just been 3-methyl. Okay? So there's 2 ways that this name could have been done incorrectly. Perhaps the die was incorrect, or perhaps we left off the locator. Is that going to change our end structure? Yeah. If the die was wrong, then what our structure should look like, I don't want to use all the color coding again, would have been that. And then that would have been 3-methyl hexane 2-ol. Perfectly fine. Get it? So when we go through and process, each of those pieces of information is really critical. That's why I think this thing in the box is really helpful, because it's trying to specify every single piece of information. Okay? And it's an attempt to color code it back with the names here as examples, so that you can try and represent and kind of pull all that information together. Kind of, sort of? Okay. Are there questions about this one?
Quick question. Would there be like a right or wrong answer if you pointed out both? Where you were like, well, there could be missing a 3 /
So, like, if this was an exam question, this could work as like a show your work, because it's, you can't just look at, well, you might be able to just look at the name and be like, I need a 3, or I need a die. Okay? Sometimes you won't see it explicitly written out, you have to draw the structure. So this could be a show your work or explain kind of thing, and you could just say, well, there's only one locator, which means the die is wrong. Or
it's missing a locator?
it's missing a locator.
Okay.
Both of those would be perfectly acceptable individually. They'd potentially be even better together. Okay? And if I had that on a show your work, explaining both explanations, I would argue is probably extra credit because that's taking it a step beyond just what's wrong with it.
Okay.
Make sense? Other questions about that one? Okay. What I want to backtrack through real quickly is Katie's comment about the functional groups. So, if we process out, and since we aren't looking at a cyclo, I can delete the cyclo thing down here. We had hexane, 2, all. Okay, and if we break that out, we had the hex, then we had the an, which is our hybridization. Okay, if it's just alkanes, just a carbon chain, that's it. Okay, I would end in the with the E. If there's a higher priority functional group, I change it from A and E to just AN. Kind of, sort of, so far? In this particular case, we're looking at it's AN. I don't see the E. Why not? There's an all. There's a higher priority functional group. Okay, what's the higher priority functional group? Well, now we could go through and look at these endings and go, oh, an all. The all is the higher priority functional group. I need to know that the all is an alcohol. That's all nomenclature. I think that's all fair game for the test. What does an alcohol look like is the next question. Okay? So you should be able to process out these kind of pieces. Okay? And you're looking probably alcohols and lower. The aldehydes, ketones, that'll be later stuff in the semester. Okay? But alcohols and lower, I guess higher on this, depending on how you want to count it out, okay, are relevant for the exam. And for this first exam, we're probably going to sit alkanes, ethers, and halides for the vast majority of the nomenclature stuff. Okay? You might see one question looking at our alkenes, alkynes, and one question bringing in the alcohol. Okay? So how do you know what an alcohol is supposed to look like? This is due to a reorganization that I decided earlier on in earlier on in prep for the class. And quite frankly, I think it's coming back to bite me. I think I needed to have talked about functional groups because it hurts for nomenclature. But what that comes back to is then this thing, you need to know what those functional groups are. Okay? For this test, this slide will be on your test. I will give you this. I will not give you this. You need to be able to process all your nomenclature pieces. But this I will give you. Okay.
That one and the other one.
This one only.
I thought you said you would give us the other side.
This
That-
slide?
That's
You're
what
not-
we thought you were talking about
We
earlier.
thought you, yeah.
no,
Okay, so you're not
Get
giving
down.
us
I'm
that.
not giving you that one.
Okay.
No.
So we have to.
Because the number of carbons, that is critical.
Yeah, no, but I.
You
want
need to have that memorized.
That, I get that.
If you want to talk about the red box,
Yeah, I'm talking about the red box. I understand needing to know the carbons, but.
send me an email about the red box. I'll think on that one. Fine.
I don't care, I just need to know what to memorize, you know?
Just the first one and then the red.
I would love that red box in the test, that'd be super cool. Or
So-
just tell me.
I'll give you functional groups, and I'll give you the center big red box. You need to know your number of carbons. You need to know what cyclos mean. You need to know how to put together a name. You need to know, I forget what that one is. Oh, the organization of highest priority for your name. But I'll give you the red box because this is pretty intricately tied to what the functional groups are. So I'll accept. Does that make sense? I would like someone to tag me with an email on that so I don't forget that, because I don't want day of the exam to have to draw it up on the board. because I forgot. Okay? Nomenclature is something that just takes practice. We'll escape out of this real quickly. If you take a look at, just to make sure everybody's aware of this, come on, get bigger. If we look at our Unit 1 exam, that first link, this pops up with, I think ballpark, I think this is going to be pretty accurate, all the topics that should show up on the exam with roughly how many questions. I will not promise that we're exactly those questions, but it should be pretty close. Okay? So if we get to naming, we're at 5 questions. So if you think through how I talked about it, I said we're going to be alkanes and lower, so the alkanes, ethers, and halides for the majority. So majority of 5 is 3, 1 alkene, alkyne, and then 1 alcohol. Make sense? Okay. So make sure you check that out because that should help you kind of get a feeling for what's going on within it. I will say the types of bonds, actually no, because we did talk about ionic polar, nonpolar as being kind of a review question. So you can expect a question on that and then differentiating sigma versus pi for sure, because that comes out of our hybridization theory. Okay. The rest of the stuff on here I think is ballpark pretty accurate. If you looked at this or printed this a while ago, as in more than a week ago, it has changed because I opened it up and it had a thing on functional groups. And I moved functional groups to the second unit. Okay, just so you're aware. Make sense?
Is there a practice exam you'll be able to print?
I don't really have a practice exam. I need to actually sit down and look at the exam. I would expect Friday I might post some more stuff. Okay, where I'm going to start is looking at that homework document, the extra problems document that I set out, and I'll be looking through there because I know you have access to those, and I'll start to qualify back to these and can use those as well. Okay, I asked a question about this. How can I subtly change this structure so it's new? How can I reward students for having done all this work by copying direct questions from it? That kind of thing. Make sense? But yeah, will all the questions be things you've already seen? Questions you've already seen? No. Will it be content? Yes. Okay. And at any point you disagree, that's okay. Let me know. And then, yeah. Saw how friggin' flexible I was on stupid red box. Jerks. I mean, you're not jerks. You're nice. Okay. But if you challenge, there's the possibility. If you don't challenge, you're going to get whatever I feel like. Make sense? Okay. It was a proper challenge for the record. Still don't like it.
I challenged, so I felt good about it.
What we're going to move to now, okay, is kind of talking about where we ended. What was it? Thursday? Wednesday. Today's Wednesday.
Monday.
So where we ended Monday. We were looking at turning our molecule from the side and getting a view on it. Okay, and so we've got images like that are shown down here, and those can be kind of challenging to view. But what we're taking is effectively a model, right? And all we're doing is turning at it and looking at it from the end, so that that bond disappears. When we look at a specific structure where we disappear that bond, we should see kind of a propeller in front and a propeller in back, or a tripeller, whatever, in front and in back. And what we should notice also is because it's a sigma bond that connects them, you can freely rotate. Okay? And as we freely rotate, hopefully what we see is that we can change where the electrons from our bonds are located. And initially the bonds, or in this particular configuration, okay, where they're perfectly overlapped, is we've got our electrons in the same plane. There's a slight repulsive force there. The electrons can't really repel away by pulling outwards. They can really only repel away by twisting. And when they twist, they can then move into a configuration where those electrons are now occupying alternating planes around us. Everybody kind of see that and understand what's going on with that structure. Ooh. All right. What this boils down into is what we would reference as Newman projections. And what we talked about on Monday is that since these are now different energies, because we have our electrons in the same plane versus in alternating planes, that they have different energies, and because they have different energies, we now have to come up with different names. Those different names we would reference as eclipsed, because all of the bonds directly overlap, versus staggered, because they're alternating around. 2 R's?
2 G's.
I did that, so,
Oh. That's right.
okay.
What were the ones you said
I-
to define eclipsed was staggered? Wait,
No,
staggered.
eclipsed
Eclipsed.
is one configuration,
Yeah.
staggered is the other.
And is there a certain, anytime they're not perfectly staggered, it's considered eclipsed?
So there's an interesting question. So we'll aim this at you first, and then maybe it'll be enough that everybody else can understand it, and I don't have to aim it at them. If we take a look at this structure, okay, are we staggered or eclipsed?
Just staggered.
Staggered or eclipsed?
Eclipsed.
Staggered or eclipsed?
Eclipsed. Staggered.
Okay, so based off of your interpretation, what I'm hearing is staggered is the instant they are completely opposite each other,
Yeah.
and eclipsed is all other points.
Yeah, but I'm sure there's a variety of other names for those points.
No. What's that?
I said, okay, I'll
Okay. And so it is an interesting kind of question. And so what we'll do with that is let's think through what's happening to the energy of our structure as we manipulate. So if we start eclipsed, and for the moment, is the colored balls bothering anybody? Okay. If we start here, where are we? High energy or low energy?
What, are we starting,
I don't know.
are we starting eclipsed or staggered?
Is there more
That's eclipsed.
energy? They're
That's
gonna
eclipsed.
push each
That's
other
higher.
away.
Okay, so
So
they're
is that
eclipsed.
gonna be less energy because they're farther away?
Are these farther away?
No.
Okay, so they're eclipsed. Is this high energy or low energy?
High.
High because they wanna push each other away?
Okay, it's high energy because they're like, get me out of here. It's that high stress state. Okay, you're locked into that box. Okay, so for instance, if you came into this classroom to have this class, and I said you can only sit on the edge of the table, and you can't move. That's going to be a high stressed environment. Okay, that's effectively what we're talking about here. We can look at that energy as a stress. You want to expand and release. Okay, occupy more space. So we are starting at a very high energy place. Okay, so let's consider kind of a rotational system. Okay, so we're going to reference energy, E for energy going up, and then on this axis we'll talk about our rotation. Okay, and we're starting high energy. Oops. Okay, fraction of a rotation. You want to run the front or the back? Back, okay. Because you were talking. Is that high or higher energy or lower energy? Okay, what do you think? Is that higher energy or lower energy? Higher energy or lower energy?
I'd say it's still high.
Okay, we got to be a little bit careful. I said higher or lower. You can't tell me high, because I don't know what high is. Okay, we're either starting at Everest or the bottom of the ocean. So you think it's lower.
Yeah.
than where we were?
Lower.
Keziah? Higher or lower? Katie?
What?
Higher or lower?
Then what?
Than where we started.
Where do we start? Where we lined up?
So there's an interesting question. Where did we start? I did such a subtle change to the rotation that it becomes very challenging to narrow that down. That's where we started?
Okay, that's, so if you move it like that, it's a little bit less energy.
Okay, so everybody else said lower. Why do you want to say higher?
Just felt right.
Just felt right. That's okay. Okay, and this becomes one of the things that we have to think through, is that we will have a gut instinct and response. You have to be able to defend that response. And if you can't defend it, that doesn't necessarily mean you're wrong. You are, in this case. Okay? But you need to come up with that defense.
I guess I
Okay.
feel like I had a 50-50, because right, if you turned it the other way, right? Isn't it
Okay.
higher? If you just slightly went back and then turned it the other way.
Is that higher or lower than where we started? Here's where we started.
Also, then higher, right?
That's higher or lower? That's higher?
Or is that wrong? It's not?
Is that higher or lower? That's where we started.
Lower. It's lower.
Lower.
Because I,
Higher.
Lower.
Katie,
I'm sorry, we didn't need to say the first one again.
right there
Okay,
to there.
it would be the same, it looks the same to me as the other one, but just a different.
Okay. Answer my question though. Your description's lovely, but answer my question. Is it higher or lower
Than where it was before, it's.
than where we started, right
So
here?
that's the highest energy, and now that has gone a little bit lower.
Okay. So, because you jumped in now with a higher, throwing support behind Crystal. That's nice. I like it. Can you tell me why here, or is this here, why this is now higher in energy than where we started?
I just thought since it was going the opposite way, that it would be.
Ah, and so that's lovely. Okay. So you're adding that explanation in. It's not true though. Okay. So why is it high energy here?
Because they're matched up, isn't it?
The bonds are matched up. Why is it high energy here? Because
They're equal.
I don't know what equal means.
Like she said, the ones are matched up.
I accept. Are they equal here? Does that make them more stressed because they're interacting more, or are they interacting less?
Less.
If they're interacting less, what happens to the energy? It goes down. Okay? So if we rotate one direction versus the other, what's the net result? It's still getting lower. Okay? So if we start at our high point, we can go rotate kind of the opposite direction or the other direction, and it's still going to go lower. Okay? So we could look at these as kind of data points. Whoops. Bringing the eyeball back. Go away, eyeball. Okay. Okay, Crystal, we're starting it off with you. Is it still getting lower? Tell me if you're like, no, it's getting higher. Oh, you're breaking mine. Okay, interesting. As I continued to rotate, what happened? We started high, and then it got lower, and now we're back high. Is this higher or lower? Whoop, where's the depth perception? One eye. There we go. Then here.
Aren't I paying attention to the colors of the font at all? Because that's what Matt, right?
I
Okay, no, we're not,
asked.
okay.
I asked, and
Then-
you all said it didn't matter. Okay, there's where we started.
Yeah. It's not even-
I didn't ask it high again. I asked, is it the same as where we started?
Yes.
Ooh. So I did this rotation. So everybody see this? Here's where we started. We'll kind of hit the sort of the three of you at the same time-ish. Make it all uncomfortable for all three of you. And we go, we're right back to where we started. Sort of all three of you. rotate, poof, right back to high energy again. So we're starting at this high point, and then we're all of a sudden at another high point. But somehow we got lower in between.
This is a circle.
But I can't get any higher than those black lines.
This is a circle, so it just goes around and around.
How do I do a circle that doesn't go higher than those black lines?
Well, you draw the line the other way.
So I just do this, that's a circle?
No. The peaks or the curved part should be touching the line. Just draw a circle between the lines and the dashes and the lines. Just draw a circle. Just like this.
Okay. So there's an interesting idea for that circle. Is this point
Well, it's
on
not
that circle?
a perfect circle.
Okay, well,
You could mix your dimensions of your dashes and your right angle scale.
can I draw a circle that has these 2 points on the circle with nothing higher than it?
If you put them closer together.
I can bring them real close together. What circle shape am I going to do?
An oval.
Okay, even ovals go up and down. I could pick here and here. All of this is above those. I could pick right here and right here. This is above those.
I don't get the argument that you're trying to make here.
There's no argument. I asked how they were related to each other, and you said draw a circle. I'm not arguing. You're arguing.
I don't, but what are you,
How do we connect those points?
that's, yeah,
Okay.
okay.
And so where we started was crystal, and you said draw a circle, and I said drawing a circle is not going to connect those points in a way that actually makes sense. There's our starting point, right? What happens as I turn? What happens to the energy?
It's going down.
It's going down. Tell me when it stops going down. Oh, you're going to jump in front of the bullet? Okay.
Thanks.
Why did it start going up?
Because it's moving towards the other.
As we start this rotation, the bonds are all rotating away from that front bond. So this back bond here is rotating away from this one. Rotates away, which means it goes lower. And then eventually what happens?
Goes higher.
It's going higher because why?
It's rotating it.
Just trying to reach the other one.
It's starting to get close to the other bond.
So it's
That's what's causing it to go up. Which means this goes down, this starts going up. There's an exact point at the bottom of this where it is as low as it can possibly be. Who wants to try?
Try what?
Figure out where that low point is.
Like the lowest energy?
Oh, yeah.
It's gonna be, is it gonna be like an angle or a degree?
Is it like 1S?
Technically, it is an angle and a degree, but we don't even need that. I'm going to say Kimball's going to do it for me. You ready?
Yeah.
So there we go. High energy state. Lower, lower. Have we started getting higher yet?
Right there.
Ooh, right there. Okay. What does that look like to you? Is that eclipsed?
Yeah, it's not.
Is that eclipsed?
Oh, wait a minute.
No, what is it?
Staggered.
Oh, it's staggered. When we look at this diagram, this is eclipsed. This was eclipsed, and we could call it eclipse. That says eclipse, trust me. New. It was a new eclipse because we rotated. What's this bottom point?
Stagger?
That's our staggered. It's the well. And as we continue to rotate, what happens?
It's going back up,
It goes back up. And then as we continue to rotate,
goes back down.
it goes back down. And we're seeing alternating between eclipsed and staggered. Okay, there's a couple important things to note here. Staggered exists. Eclipsed does not. What is the difference between staggered and eclipsed?
Eclipse has more energy because they're closer together.
It has a higher energy, yeah.
And if it was just an or a molecule just out there in the wild, wouldn't it would always want to be away from each other.
As soon as we're eclipsed, what's happening?
You're forcing something.
It's immediate, like, nope, leave me alone. If I line up eclipsed the other way, oh, nope, leave me alone. So eclipsed, as soon as we get to that point, immediately shifts away. What happens when I get to staggered?
It's chilling.
Yeah, because I start to rotate and go, oh, nope, I don't want to go higher energy. Rotate the other, oh, nope, I don't want to go that way. So you get kind of a steady state and this well, the lower energy state. Okay, what we're talking about here at these maximums or these peaks are transition states, and we can use a double dagger for those. We'll bring in transition states as a word in the next unit as well. Okay, and depending on what chemistry you had, Kimball, did you have 151 and 152?
Just 151.
Okay, so you didn't hear about. Did anybody have 152? You did? You remember transition states? Ah, I'm gonna yell at your gen chem instructor.
Is that the leaf quiz?
Don't worry, don't worry about that. We'll bring it back in. Okay, those are transitions. The valleys are existing states. Okay, so if I'm going to talk about which of these two is most important to me, the one I'm going to talk about is the staggered state, the valley, because that's a valuable thing. The structure exists, quote unquote, at that point. I can give it energy, and it can rock back and forth within this well. It can go up, I can go a little higher, I can go a little lower, I can go a little higher, but its steady state is at the bottom. If I look at the eclipsed, what happens? When I get up to the eclipse, it's like, nope, F this, and starts to roll the other way. Or roll back. So you can envision it almost like a ball on this curve. The ball is never going to sit at the eclipsed point because it's a peak. It's going to roll one way or the other. But a ball could sit in that staggered state, that valley. And when we look at this for this particular structure where the colored balls didn't matter, all we're going to get, that's supposed to be equal all the way through, is just these equal peaks and troughs all the way down. Okay? And if we look at that rotation, we could run from 0 degrees rotation all the way through 360. Okay, of course, I did align that wrong. Okay, and we could label out what happened at each of those degree states. Okay, which someone started to mention degree states. Like, okay, well, how many degrees is the staggered? I don't care.
Okay.
I really don't. Okay, all I care about is that when you rotate, you're moving into a staggered or more stable state.
And staggered is more stable because that's where they want to be. Because it's lower energy.
Why is it lower energy?
Because there's no tension of them wanting to get away from each other.
Lovely. The electrons are in different spaces. Everything's happy and beautiful and lovely. Okay? So, right? Makes sense? What happens when I add colored balls?
Everything changes. They're going to have different interactions or
So if
one's
I look,
going to go more quickly.
okay, so now and you're right, we're starting to add things in. Which state should I start looking at? Should I look at the eclipse state or the staggered state?
You should start at staggered state because that's low energy.
I want to look at the staggered state. The eclipse states aren't relevant because they're the peaks. I want to look at the valleys. Okay? So, eclipsed or staggered?
Staggered.
Sorry, repeat the question.
Eclipsed or staggered?
Oh, eclipse. I mean, sorry.
Thank you. Okay. So now what we're going to do is we're going to rotate. As we rotate, what happens?
Becomes eclipsed.
Everybody understand it becomes eclipsed, just like it did before. Okay, but we don't care about eclipse. Let's continue to rotate until we get to our new staggered position. Right? Do you see it as staggered? Everybody see it as staggered?
Yep.
Let's try that again. Sorry, because
Yeah.
Okay. So now we're staggered. Is this staggered the same energy as this staggered?
No.
Oh, that was awfully fast. Why?
Because in this staggered, your blue and your red are closer together.
Yeah. So when we're talking about adding on these colored balls, we are making an assumption here. You are making an assumption that this red ball is not the same thing as what's out here. Well, what's out here?
I don't know. There's no color.
Well, if there's no color
Oh,
out
it's
there.
a hydrogen.
Ah, which means this thing is,
Carbon
could be.
or hydrogen.
Could it be a hydrogen?
I don't know.
If it was a hydrogen, shouldn't I show it the same as this that you just defined as hydrogen?
Yeah.
Yeah. So it's not hydrogen, it has to be something else. What something else is it?
Oxygen.
Okay. What's the difference between oxygen and hydrogen?
Oxygen's more electronegative.
True. Keep going.
Um,
More fundamental. Remember, this is unit 1. What's the difference between oxygen and hydrogen?
Electron levels.
oh,
I mean, yeah, they have more orbitals and electron levels, but
Counter.
ultimately they have more because they have more electrons. Okay? So this red group has a lot more electrons. So when we looked at the staggered and eclipsed initially, we didn't care that there were hydrogens out there. What was repelling away? The bonds. That was it. I don't care what's out there. Now there's something else out there. And that something else is now creating a different interaction. Well, what's happening with the blue thing? Is that a hydrogen? What do you think, Crystal? Is that a hydrogen? No, why not? What did we say was a hydrogen?
What's not?
No, not there. Okay, I've got a ball there, which means
Yeah, this is not
not hydrogen. What is it?
that now being.
Okay, it's a carbon. What's the difference between carbon and hydrogen? It's a different element. How is it a different element?
Electron negative.
Be more positive. Drop the negative.
More electrons.
Carbon has more electrons. So if I'm now looking at these, I have a group with a lot of electrons and a group with a lot of electrons that are staggered, but they're kind of close to each other, right? They're kind of awkwardly close. Whereas if I do this,
that's probably the most stable.
this is probably more stable. We've got our large electron groups as far away from each other as possible. Okay? And now we'll go for the inappropriate side of today's lecture because it's always fun to bring this in. I blame past classes because they brought it up. Okay? We have different energetics between these, so we need names associated with them. Okay? So, and here's where it gets mildly inappropriate. I don't know about women bathroom etiquette, but I know a little bit about men bathroom etiquette. So Kimball, here, you might be able to chime in as well. Okay? You go into the bathroom, there's a line of urinals, right?
So interesting.
Someone's standing at a urinal. Which urinal do you pick?
The one that has like a space in between it.
Yeah, you try and go as far away as possible. Okay? You don't piss in the same urinal. That's a really high energy state. That's a bad idea. Okay, so you go as far away from them as possible. Okay? Believe it or not, there's a whole lot more levels to this bathroom etiquette. It's an interesting meme. You can look it up if you're really curious about it. Okay? But it's apparently something that all men know. It's just bizarre. Okay? But you don't go right next to them. Why not?
Because that's weird.
That's weird. Some might call it awkward. What's French for awkward? Gauche. So if we're going to talk about these interactions, they are staggered, but this interaction's a bit awkward. We're going to call this the gauche interaction.
That's really what it's called?
Yes, legit called gauche. 100%.
And you just know because,
They're a little close to each other. They aren't.
but it's not necessarily defined by the atoms, specifically which atoms.
It's, ooh, good point. It's true. If we look at this, okay, my right hand now, referencing my right hand, these two, what is the interaction between them? Are they staggered or eclipsed? Cool, they're staggered. Everybody get it? See staggered? Are they gauche?
Yeah.
Is it like gauche and super gauche?
It is gauche. There isn't a gauche and super gauche. But is there anything we could do about this gauche with them being hydrogens?
No, but they're just have this.
No. So that energy is always going to be there. That's always going to be a kind of counteracting energy. But this energy is a much larger contributor. So when we talk about gauche, it can officially apply to any two groups. But as a blanket statement, it doesn't make sense to talk about the low, smaller atoms interacting that are gauche. It matters to talk about the large groups. So the groups with the most electrons. Right? When I asked you what atom was red versus what atom was blue, there was a lot of kind of like, I don't know, and you're freaking out over the choice. It was anything other than hydrogen. What do all elements have in common in comparison to hydrogen?
More energy levels? More electrons?
More electrons. So it doesn't matter what I put in there, it's always going to have more electrons, so it's always going to be the dominant interaction. I don't have to worry about the hydrogens anymore. Okay? And if we go, stupid ball, we turn it all the way around to here, now they're on complete opposite sides. Right? They're as far away from each other as possible. Okay? We don't have, I would argue, as equally awkward a name about urinal references and all that. Okay? But this one's known as anti. Opposite sides, anti.
Where is anti in the journal status? I have a 10-year-old, so I gotta fill him in on this.
Anti is you go as far away as possible.
Okay.
Okay? It depends how many urinals becomes the problem.
Ooh.
You go into a bathroom with 3 urinals, you just make sure there's one in space. If
But
you got
is it-
20 urinals, it's like, I'm going to go
Is
as
it
far away as
gauche
possible.
to walk in and stand there and try to decide which one to go to? You need to know instinctually.
Well, are you making eye contact?
I have to
If
teach
you're
you.
making eye contact, that's pretty gauche.
Make no eye contact and just head down, head down.
Look up urinal etiquette. It's
Okay,
interesting.
I will.
It's fascinating because I actually watched someone go through like, here's 3 urinals, here's 5, here's 6.
Follow your gut. That's
And
what
every
I'm
single
saying.
time, like I was doing exactly what the authors were saying that you should do. And I was like, how do I know this? This is stupid.
Male brain.
Should be
Okay.
yeah, should be
I mean, is there not a similar thing with women? You got a whole bunch of stalls. Do you
No.
try to avoid?
No, you look for the one you think has the least amount of germs.
Yeah, the least used.
Yeah, you're like, which one's the least used? Contamination, that's it.
Okay. Well, sorry.
Which is statistically the first one.
Yes.
That's what people typically avoid.
There are memes on this too, just.
Really? The
Yeah.
first one is
Yeah.
statistically the least
Yeah,
germy?
because instinctually you think, oh, everyone goes to the first one, but really, it's
They don't.
not that used.
So
It's
people
always
will
the
skip
cleanest.
it,
Yeah. It's
so
always
then
the
it gets less
Okay.
used.
You learn every day. Okay, so we getting it? Okay. So if we push kind of beyond this, really what we're talking about in this kind of organic chemistry sense is that we move on to butane. So with butane, we have 4 carbons, okay, and we talked about our structures for butane. We could do that kind of zigzag, or we could do the kind of C shape. That's an awkward C shape. Gauche C shape. Okay. Which I think 1, 2, 3, 4. Okay. So there's our kind of gauche C shape. Okay. Or it looks gauche, but if we turn, it's now what bond do we sight down? What we're trying to do is sight down and see the energetics of the shape. What bond rotated when I did this? They're all carbons, so you got to do better than that.
The sigma?
Which sigma? I got 3 sigmas.
Oh, 1, 2, 3, the third one. Wait, I'm starting from the right. 1, 2, 3. No, the other one. My right. Yeah, your left.
1, 2.
3.
So that's an atom. What's the
Oh.
sigma bond that rotated?
The center one.
Yeah, right there, right? That's the sigma that rotated. Everybody see that? Okay. Which means if I'm going to move this molecule and look at it from the side, and I want to do my Newman projection, that bond is the bond that needs to disappear, if we will, in our Newman projection. So when we turn and look at it from here, Has that bond disappeared for you? And if you're doing this, yes, it disappeared for you. Okay, everybody see that that bond has disappeared? What configuration are we in? Staggered or eclipsed? We're eclipsed because you have to do this to see everything, right? Okay, is that a high energy or low energy? High energy. What happens? There's our zigzag. If we move here, that bond has disappeared, right? What's eclipsed? You're saying partially eclipsed, so tell me what bond is eclipsing what bond?
I just can't see this.
So that bond, remember, that middle bond is the bond that must disappear in a Newman projection. So that's not part of the eclipsing interaction. The eclipsing interaction are all the bonds on the outside.
So it's not eclipsed.
Okay, so what is it? Because yeah, it's staggered. Okay? So why do we draw our structures as zigzags instead of doing this weird C shape? It's the lowest energy way to represent the molecule. That's why they're drawn as zigzags. Okay? Not just because they look pretty, it's because they're lower in energy. And when we draw things, we try to draw the lowest energy state. We don't want to draw the highest energy state. Newman projections allow us to see that. Okay? So cool. That sets up our staggered. Okay? Do better. Is this still just staggered, Crystal? Can you do better than staggered? No is fine too. I'm okay. No?
It's the lowest.
Annie? That's a good word. You should have used that more. Can you do better than staggered?
Can we turn the neck one back?
You want me to turn one just to help a little bit? Do better than staggered. You can say no. Katie.
I don't feel like you can do better than staggered because
You're wrong. Nobody?
Anti?
These two groups, our large groups, are on opposite sides of that bond. If we continue to rotate, now what do we have?
Gauche.
It's still staggered, but our two groups are gauche. So we do have, as soon as you add more atoms to our structure, we do have the opportunity to now define beyond staggered. Which is why when we look at butane, we don't want to reference this as staggered. Because this is staggered, that's true. But so is this.
Would you say like,
And they're very different energies. Go ahead.
if it was like, tell me what this is kind of thing, would it be like, it's staggered at an anti-level? Or like, how would you word that?
So I could see it as, in a couple different fashions, I could see it as a multiple choice saying, which of these is the lowest energy?
Okay.
Okay? Or which of these is in the anti-configuration? Which of these is in the gauche configuration?
Okay, so it wouldn't be like staggered, anti, like you're not just gonna keep building onto that, it's gonna just fall in one of those four names.
Which is a fair play. Okay? So if we look back to where we started, we had eclipsed. I think this is what you're asking. We had staggered, and what we just discovered is that our staggered can split out into two other categories. We can get anti, and we can get our gauche. Okay? Can we technically get different eclipsed? There's one eclipsed, right? Everybody see that eclipsed? Is this also eclipsed?
Yes.
Is it the same energy?
No.
Damn. Which means, what could the eclipse potentially do?
Split off.
It could split off as well. Okay? I don't care. Are there names for it? Yes.
We don't have to worry about it.
I wouldn't worry about them.
Okay.
Okay? And you might see them in a textbook. I honestly don't know. Everybody has different slightly opinions about it. Okay? But why should I not care?
Because it's the high energy, unstable.
It's the thing that doesn't exist.
Doesn't matter.
Okay? Why do I need to go through and name those extra things when they don't actually exist? they're not at a stable enough state to have any real appearance. Okay? So I can go through and define them, and I should be able to say, this is lower energy staggered than this. Absolutely fair game. But being able to name it, no. Don't care.
Okay. And you have to have two to compare anyway.
Typically, you have to have two. Yeah. Okay? So cool. We ready for the next thing? Go for it. No?
Where did you define anti? Is just the opposite of gauche?
Anti isn't the opposite of gauche. It's where our two groups are opposite that bond. So if we look at our anti, we've got an atom X and an atom X. They're opposite each other in the drawing.
Okay.
In gauche, they're not opposite each other. Okay. If we look at this one right here, let's take a look at that gauche with the model. Right? Is that gauche? Is that the gauche that's there? Everybody see that is the gauche. Okay. Is this still gauche?
Yes, because you just flipped the whole thing around.
And this does become a difficult concept for people to manipulate as well. Is you'll see this and say, oh, that's gauche. This drawing is an artifact of whoever's drawing it. They feel it's easier to see this on this left to right system. But it could just as easily be a flip of the molecule and showing that same interaction at the bottom quadrant, okay? Or the other bottom quadrant, or the top. Does that make sense? This goes back to there's no up, there's no down. That, as long as that interaction, that proximity is there, that is a gauche interaction. Okay? Okay. Rewatching this video, if you do end up doing that, you're probably going to struggle a lot because all you're going to hear is me talking through this. Okay? What's really powerful is having the model kit to be able to see those relationships. And that's where dealing with these is going to become important. Okay? Which is going to bring up kind of the next issue that we could push on this. Okay? We went from a side view, our C structure, or our upside down boat, if we will, structure, and we said that became our eclipsed configuration, our eclipsed Newman projection. And how we've got this drawn, CH3, bit sloppy, but you guys get the idea? Right? So we had to convert between a side view to the Newman. Which means I can ask the question, here's a side view of a molecule. Draw it like a Newman projection. You have to be able to make that conversion. Or I could say, here's a Newman projection. Draw it from the side. What is it going to look like? Okay? Running a little short on time for where I wanted to get to. Sorry. If we drew this from the side, how do we do it?
With lines and dashes, or wedges and dashes.
Okay, we're going to have to be real careful with specifying our wedges and dashes. The other thing that's going to become important, are you looking at the molecule from the left side? Or are you looking at it from the right side? Because it's going to look slightly differently, right? Which side is my hand on? Left or right?
Right.
Ah, there's the word. You're right. Okay? Because is it on your right? No, it's on your left. So depending on which way you look at the molecule, your drawing needs to change. So you have to be very careful with how you would represent that. Okay? So if I look at it from that side, what I'm going to do is grab this atom, and I'm going to pull it this way. So that my eye that's on the left that's my right, whatever, on the left comes to the front. So now when I look at it, there's my red dot carbon. And what do I have? I have the hydrogen coming straight down. I have a wedged bond coming out, and a dash bond going away. Because I pulled this carbon over here. Where's this X? Ah, there we go. The X would be wedged. That's a hydrogen. Pull this out to our back atom. Our black back atom we'll call as a blue dot. Going straight up from that is our X. Okay, we're going to have another wedge and a dash. And that wedge and dash, in this case, isn't going to matter because they're both hydrogens. We'd have those drawn on as hydrogens. You need to be able to do those manipulations.
Model kits?
Okay? Is this vastly easier with a model kit?
Yeah.
Yeah. It's a hell of a lot easier with a model kit, so I would recommend that you practice with a model kit. Are you allowed a model kit on the exam? Yes.
Yes. Yes?
Yes. Do you want to use the model kit on the exam? That's a harder question, and I would argue no.
Why?
Okay? Because it takes time. So what you should be doing is practicing these types of questions with the model kit right now. The whole point of practicing them with the model kit is to do what?
Become faster.
To understand, to be able to visualize it in your head so that when it comes to the exam, you don't have to build the model, because building the model takes time. Okay? That's one of the things you got to watch out for. Kind of make sense? Okay. And speaking of time, I know we're a little bit short on time. God, why won't that bond fit nicely? What a putz. Thank you. Seriously. Oh, I hate you. Okay. Where we're going to go from here is really some next level stuff. Because what's going to happen is we're going to continue to expand, ultimately going up from butane. Here's that rotational thing we're talking about. They've got numbers and quantification. We don't care about quantifying, we just care about those relationships. You should be able to go through and generate a graph like this. Again, don't care about the numbers, care about the relative peaks and valleys. Okay, you'll note that it changes from when we just had 2 carbons. Why? This is the introduction of the different staggered and technically the different eclipsed. They're different peaks and valleys. Okay? Our cycloalkanes. The cycloalkanes become a little bit more challenging to deal with in this respect, okay, because the ring prevents the rotation. And if you prevent the rotation, well then why do we care about Newman projections? Well, you don't, for the most part. Okay? When you move through cyclopropanes, butanes, and a little bit the pentanes, there's very little rotation. The cyclopentane actually has a little bit of wobble. But the propane, if you want to keep your model kit, don't build it because it's a very stressed molecule and it will probably break your model kit. Okay? The butane you can probably build, but again, equally a little bit on the stress side. And what you'll find is that if you try to do a Newman projection, almost universally, everything is eclipsed. That's high energy. That's bad. That's one of the explanations behind them. And when you move to the pentane, you'll find it doesn't actually like to lie flat. It starts to pucker a little bit. That pucker is to alleviate some of that internal stress. When we move up to the 6-membered ring, all hell breaks loose. And we get a nice 6-membered ring. And what we'll find with the 6-membered ring is you can actually do some rotations. Okay? Those rotations, if we look really carefully, let's take a look at this blue and this black ball. As I do that rotation, what do you notice about those 2 positions? Yeah, they kind of move back and forth. And you might be like, well, who cares? We care, actually, because when we look at a cyclohexane, what we'll find is we can form what's known as chair structures. And when we look at these chair structures, it has an interesting feature, okay, with these bonds. So here I'm sitting in this chair, and when I sit in this chair, I'd be facing that direction. This is where I put my back. It's where I sit, where I put my feet. Kind of, sort of? I'm gonna take it as a yes. I'm gonna take my back. Where I put my back, it's a fun chair. It's a little lounge chair. I'm gonna turn that into where I'm gonna put my feet. Because I'm lazy and I don't want to turn the whole chair around. I'm gonna take where I had my feet, I'm gonna pull those up. Anybody notice anything interesting about what happened to these groups? So there's one configuration. You ready? We'll go back the other direction. Come on, you jerk, work with me. Okay. We might run into this farther apart here. You might say, they're really close to each other. And if I do this model is fighting me all the way. I don't know why it's doing that. They're usually much better about this. And here you might say, they're really far away from each other. So all I did was a little bit of rotation, and we saw a massive switch in the location. And if we're seeing a massive switch in the location, what does that mean? Energy differences. Really big energy differences. Those energy differences are what we'll refer to as axial. We're sitting in our chair, it's the up-down from our chair, versus equatorial. And you saw a video on this already that you were probably like, dang, I don't understand what's going on. Versus equatorial, where it's kind of coming out from the seat of the chair, more or less. Okay? We're going to play around with those on Monday before the exam. We'll limit some of the questions on that content because you haven't had a whole lot of practice with it. And then the last thing that I want to point out,
But the exam's on Wednesday, right?
it is on Wednesday. Because believe it or not, all of this stuff is technically just application of what we've already talked about. This, remember we talked about E and Z? And I said there were rules that helped us to establish E and Z. Ta-da! Priority, assigning priority is right here. Higher atomic mass. We didn't find a difference. What did we do? We moved to the next atom. Still no difference. We continue to move through the chain until we find a difference. Okay? You use E and Z as a system just like you will for chiral atoms. Chiral atoms will be the last thing we talk about on Monday. So we'll do a little bit of hexanes, cyclohexanes, and then we'll also introduce our chiral atoms, which is identifying, again, we've technically already talked about it, just not to any gory detail, an atom with 4 different things connected. And what does that manifest into? Okay? That is a challenging thing to manipulate. I'm going to have to rein back on questions for chirality and probably start off Unit 2 talking some more about chirality, because it is something that's going to come back and affect us. It's a huge effect in pretty much anything biochemically related. Okay? So Monday will kind of be sort of a review, but it's going to be hitting some of these really new topics in a little bit more depth, and then we'll push to where you guys have questions.
And those really new topics will be on there.
I'm just going to limit the amount of questions. So I don't remember exactly how many are there, but I would bet they were already at 1 or 2. But what it does mean is that you will see those questions show up again